the mirror material itself is just there to hold this little film of metal in place. The Pyrex doesn't participate in controlling the light. So lots has been learned recently. Here's an example of what you see when you look into the guts of, probably this is Keck, and you see these segments. Once again, each one the size of a backyard patio table, and lots of technology for keeping all those pieces in the right place as the telescope moves around. Here's kind of a human scale. There's a platform with a railing, so a human would be kind of like this big. So there are people still making monoliths. A world leader is the University of Arizona. They have something called the Stewart Observatory. Roger Angel is near the end of his career, but he's been instrumental in the developing interest in monolithic mirrors. And so you can see a scale here. This is probably an 8-meter mirror. So you have to cast the mirror, that is the structural piece of it, cast it in roughly the right shape. Otherwise you spend the rest of your life grinding it off. So the glass is put into a kiln that's rotating, kind of like the Mercury concept. And the kiln is heated up till the glass melts, and you get a little bit of curvature, which helps in the beginning process of removing the unnecessary material. So you spin this thing, get it hot, everything melts, and then you turn off the fire, and it just keeps rotating while it cools down for weeks and weeks and weeks. And eventually you can start working on it with computer-controlled polishing techniques. But it's a big deal and hard to move these things. There are many adventures associated with moving the primary mirror. So here's the concept, starlight coming from the left. Here's the mirror. So light comes and reflects off the mirror, and then inevitably there has to be another mirror. So this thing actually has a hole in it because the light that reflects from the primary mirror, this guy, hits the secondary mirror and goes through the hole, and back here we have instrumentation. And Newton this is a class of telescopes that use reflectors like this, Newtonian telescopes. There's a lot of different strategies. Here's the summit of Mauna Kea on the Big Island of Hawaii, which is covered with telescopes. The Japanese National Telescope, called Subaru, is on the summit of Mauna Kea. Today I'm going to tell some stories about my own experience with these things. So I was at a conference and sat next to the chief engineer of the Subaru, and he was Japanese, and his English was better than my Japanese, which is non-existent. So anyway, we sat next to each other at the big luau at the conference, and he was telling me, he was telling me he was on the Big Island for 5 years supervising construction of this telescope. And the strategy of the science community in Japan was that he could go to Japan once a year and visit his wife, and his wife could come to Japan once a year and visit him. So he was by himself a lot. And he decided to take up the hobby of making fruit preserves using tropical fruits. So he got interested in guava and papaya and all this stuff. And the big challenge was, what do you package these things in? Because he wanted to ship them back to Japan. And along the way, he discovered mason jars, glass jars. And at that point, the Ball Corporation, not Ball Aerospace, but the Ball Corporation was a major producer of mason jars. And and he's telling me this story, and I reached in my pocket and got my business card and showed him, I work for Ball. He was mind with excitement. I have a nice picture of the two of us standing under the mirror of Subaru. And Subaru, once again, monolithic mirror with that thin metal coating on it. And once a year, and the coating is aluminum, so it's shiny, but gradually it oxidizes. So once a year, they have to take the coating off and recoat it. And the biggest machine, single thing that's ever gone up the mountain is the recoating box for Subaru. It's a massive thing. It might be in this building here. So they take the mirror out, which is a big enterprise because the mirror weighs like 7 or 8 tons. And they lower it down and they put it in this thing that looks like an envelope. It slides in, it has sprayers with acid, and they acid wash the mirror. And then they have an elaborate cleaning process, and then it also has filaments, also in the box, that flash aluminum onto the mirror blank. And then they have to keep it clean and move it back to the telescope. Yes, sir?
Why do you have to use glass just to support it? Couldn't you use another substance if the glass is not being used for the mirror?
The key thing is stability, thermal stability. Because the telescope, every day the telescope temperature changes, and you want to be ready when night comes to do astronomy. You're going to open the dome here. You can see it's open right there. They refrigerate the interior so that it matches the temperature they're going to experience when they open the dome that night. And the material they use has to have a very low, it's called a coefficient of thermal expansion. Because when actual air gets in there, the temperature changes inside the dome, and the mirror shape will change. Am I answering your question?
Well, no, I mean, I would think of the other material that you can use. More practical to use.
There are many other, mostly there are glasses and ceramics. There's a constant evolution in the material science related to astronomy. Carbon fiber is something. But it's very easy to make, remember I said, when you cast the mirror blank in a kiln, you want to exploit the fact that you can melt the glass while it's rotating and you get almost the right shape. Otherwise you spend years removing material. Carbon fiber doesn't have that property. Heating it up doesn't make it soft enough to conform to a shape that you might desire. So, and we're going to talk about James Webb Space Telescope. It uses beryllium mirrors, which is a real challenge because beryllium is working with it is an occupational problem. It's a toxic material. So there's many adventures along the way. Now, this is a neighbor of Subaru. This is called Gemini. There are 2 identical telescopes, one on the big island of Hawaii, and one in Chile, in the desert, where there's a large collection of telescopes. So this is called Gemini because they're twins. They saved some money by having one design team, one management team, and so forth, design and build. Both of these use monolithic mirrors. They are the last of the monolithic mirrors, really. Question, comment? So here's, once again, a kind of a history of the evolution of size and time, but notice this clustering here. This is really a change in the paradigm. This is the introduction of segmented telescopes, which has allowed for a rapid increase in size, but still manageable cost. And cost is a non-trivial issue. Something like Subaru is, if you wanted to build it today, you're talking about $300 to $500 million. And there is, as I will show you, I can tell you, interrupt myself to say, there is controversy because the University of California and the University of Hawaii and the National Science Foundation want to put a much bigger telescope on the summit of Mauna Kea. And there's stiff resistance from the native community. Right now, you cannot get to the summit. In the past, you could drive to the summit. You spend some time driving on a dirt road. Do not tell your rental car companies because it's specific in all the contracts. You're not to drive up to the summit. But anyway, you can't do that now because of the tent city that has formed as part of the resistance to further construction on the summit. And so political issue has been, for 10 years now, been a source of battle. Here are the 2 telescopes that are under construction now, the extremely large telescope, which is a European construction. There was an even larger version of this, a thing called OWL, the overwhelmingly large telescope. But the European Union decided the cost of that was just too much. But ELT is under construction in the desert in Chile. And the TMT, which is the one the Americans would like to build on the island, is, not to worry, it's mine. The TMT was the 30-meter telescope, and that is completely stalled now because of the political issue of the natives on the island. So here's another kind of a detail of what you're dealing with. Here's a human to give you a sense of scale. Primary mirror, big structure to hold this thing right there, the secondary mirror. So starlight comes down, hits the primary, hits the secondary, and then there's additional mirrors to guide the beam to the instrumentation. And this is the technique used for Gemini, the very large telescope, which is in Chile, I'll talk about more, and Subaru, and they're all about 8 meters. So this is an interesting challenge if you're building a big telescope with a big mirror in order to make the thing manageable. So because all this moves during the night when you're doing your exposures, this thing is tilting and rotating. You just can't let the mass run wild. You want it to make it thin. So the mirrors that are used in these guys are about this thick, but they're 8 to 10 meters in diameter, which means, Ansel, you have your magazine there? Let me just use that as a prop for a second. Means if you pick the mirror up by the edge, it will do this. You know, sitting in its cradle, it has the right shape, but if you just pick it up, it will just sag. So that's a good thing, and it's a bad thing. It's a good thing because it means the mirror is flexible. If you push on it with a little electric motor or a hydraulic jack, you can change its shape. Because it's so thin, it's not quite like a sheet of paper, it's like a magazine. And you can change the shape, and you have to change the shape because the shape is changing all the time. If the wind blows on it, it's a gigantic sail. And you cannot tolerate motions bigger than 10 billionths of a meter. So we're going to talk about this more. Floppy means you have to keep it. You have to actively manage it. You also have to work on where this secondary mirror is and its tilt. So the secondary mirror is in a pod with all kind of motors, and it's like 2 meters in diameter, 1.5 to 2 meters in diameter, and you have to manage it, tilting it, not on the scale I'm doing right now, but you have to tilt it, you have to move it up and down, that's called piston, and you have to decenter it. So there's massive activity going on here, except it's going on a microscopic scale. If you were standing next to this thing while it's working and you put your hand on it hoping to detect some kind of vibrations, everything is moving on a scale of nanometers, or fractions of a micron. Now, scalability, I just put a little note here at the bottom. Scalability is key in this business. You want to be able to develop a mirror and be able to plan for the next generation to have a bigger mirror. And as I said before, big is better for a couple of reasons. First, bigger lets you measure more smaller angles on the sky. There's a direct relation between how big the mirror is and the angular resolution that you can achieve. A little telescope like you buy for your backyard just can't resolve, for example, details on the moons of Jupiter. Isn't that not going to happen? This can, because it's huge in diameter. The other thing is, when we first started, we talked about spectroscopy and looking at stars in other solar systems or trying to detect motion. Big means you collect more light faster. So big is altogether the business that astronomers are in. So here's the TMT, and you see the segments here. Thousands, I think it's maybe close to 1,000 segments. Here's this pod that holds a secondary mirror, and this whole thing rotates and tilts. I've been in the Keck during the day, when they were doing some alignment schemes, and I took a video. I was on a platform overlooking the telescope, so the telescope is tilting. And the telescope has mirrors, so when you look at it, you see the whole room due to the reflections. Telescope was tilting, and it was rotating, and the vertigo is just overwhelming. You cannot tell you can hear me say on the video, I've got to point the camera down to something that's not moving. And there's the floor below me, there were technicians down there. For a few seconds, I took a picture of them, mostly for me, so I wouldn't topple over. But immensely complicated thing. And the telescopes are getting bigger. Now, scalability is coming to a limit. We're working on 30-meter telescopes now. The question is, how do you go to, say, 100 or 200-meter telescopes? And we'll touch on that during the rest of our chat today. Everything is moving, and there's shape control. Here's some detail. Here's a segment of the Keck. This is about 5 feet across. And this is the mechanism under it to do several things. You want it to move so it's aligned with its partners on a scale of millionths of a meter. But you also may have to change its shape, so it actually has a mechanism in the middle. Now remember, and this is a piece of glass about 3 inches thick, 2 to 3 inches thick. And you can, if you push in the middle, you can actually change the shape of it a little bit. But when you're dealing with starlight, a little bit is important. Here's the big telescope that the Europeans are building. I'm not going to, this is available for you to click on. It's an 8-minute video.
Where are they building?
It's in the desert. It's called Paranal, which is, Chile, it looks like a piece of spaghetti. Anywhere in Chile, if you're at high enough altitude, you can see the ocean. Out in the desert, they have an ideal astronomy spot. Yes, sir?
Can that rotate 360 degrees?
Oh, yeah. Yeah. So let me tell you what astronomers are looking for. We'll do a little bit more on this in a minute. They want a dry place because water vapor in the atmosphere above the telescope interferes with the quality of how you see the sky. They're interested in a word we use for a different reason. It's called seeing, S-E-E-I-N-G. It's a measure, it's a technical thing that astronomers worry about, is the seeing at a location. And seeing implies a measurement of turbulence in the atmosphere between where they might build a telescope and space. So a terrible place to do seeing is Mount Evans. Many of you have probably driven up Mount Evans. It's above 14,000 feet. You think, wow, it's high altitude. The seeing there is terrible because it's in the flow, continental flow of air that has crossed the coast in the California and Oregon, and that air has turbulence in it. So if you put a really good telescope like this on Mount Evans, your results would be terrible.
Why fuss about Hawaii with all the humidity there?
Not at 13,000 feet. So Mauna Kea, the summit of Mauna Kea is at 13,300, roughly 300.
Why not the Mojave Desert?
Now you're at low altitude. So there's only a few spots in the world where this works out. Mauna Kea happens to be the best spot in the world. It is in the jet stream that's crossing the Pacific, but it's not continental air. It's air that has left the Asian continent, and that air has had a chance to, where the little turbules and disturbances in the atmosphere have settled out. The seeing on the top of Mauna Kea is excellent. And it's dry, relatively dry. The driest place astronomy is done is the South Pole, which is really important for a class of radio telescopes that need to be looking at the sky through as little water vapor as possible. They actually measure from the South Pole, which is also at high altitude, they measure the amount of water vapor between them and outer space on a scale of centimeters. Like if you took all that moisture and collapsed it and made it into liquid water, how many centimeters of water are you looking through? And there's a tiny fraction of a centimeter of water. And so they can do radio wave astronomy, and it's done at the South Pole. Definitely have challenges working down there. But we're going to talk about that too. So I'm going to let you, yes, it's cold. I'm going to let you look at the video. It's 9 minutes about the construction of this monster. There's a truck there to give you a sense of scale. So once again, we have starlight, primary mirror, secondary mirror. Now this one's a little more complicated. It has the secondary mirror, tertiary mirror, third mirror here, then number 4. See, what they start doing is designating them with M. So M4 is here, that's the 4th mirror. Then there's a 5th mirror, that's flat. And then over here they have a room where you can put your instrumentation. This is what it looks like. Scale. And there is a facility, there's a research institute in Munich, outside of Munich, where I used to spend a lot of time, called the European Southern Observatory. The Chilean installation is great because the site is good. Good seeing, low humidity, clear skies most of the time. It's a very productive site, but it also can see the southern sky. Until the European Southern Observatory was formulated in the 1950s, all the major telescopes were in the northern hemisphere. They were in Europe or California, Palomar and so forth. The Europeans got this idea, there's a whole half of the sky we're not seeing very well. So European Southern Observatory is a big player in building telescope facilities. So here's another picture of EELT next to the Arc de Triomphe. Yet another video, which I'll let you watch, next to the pyramids. See, this thing, that's a separate thing, and we're going to talk about that because I worked on it. Now I've introduced you to a scalability approach. You can build monolithic mirrors up to about 10 meters, 8 meters, and then you have to think otherwise for cost reasons. And segmented mirrors lead the way there, but the next big achievement was adaptive optics. And an interesting story about this, all of us are of an age when we remember the Strategic Defense Initiative, which was invented by Edward Teller and his team early in the Reagan administration. The biggest benefit, the biggest benefactor of the SDI has been the astronomy community, because the billions of dollars were spent on advanced technology for detectors. That is, up till that time, when you did astronomy, you were doing it with film or glass plates. But the rapid advance of signal detection schemes was a big part of SDI. Another was this, and when this was invented, it was a top secret. It was invented by a guy named Will Happer, who is in the administration now as a science advisor.
Until Trump fires him.
Well, Trump won't fire him because he's a climate change denier, so he fits into the. So let's not go there too far. Anyway, Will Happer was a part of a thing called JASON. And JASON is a group of elite scientists who were hired by the Department of Defense to have summer sessions where they would, most of these people were academics, so school would end in May or something. They would all go to San Diego, California, and sit around and try to solve problems that the Department of Defense was struggling with. And this was an invention that group came up with. It was top secret. The astronomers were thinking about this kind of stuff, but didn't have the resources to really bring it to maturity. But Will Happer convinced people that, you know, we should declassify this and let the astronomers know what we're doing. So the scheme here is, if we have we're gonna look at a dim star, and the atmosphere above you, no matter where you are on Earth, the atmosphere is moving around, and, you know, twinkle, twinkle, little star,